right, here we're going to start with page 11 of the MCPS Algebra 2 exam review packet. And here they're asking us to solve exponential equations. So we are looking for the value of x that makes these equations true. Notice that your answer must be exact or expressed as a decimal to 3 places beyond the decimal point. Okay, so the first thing I'm going to do is I'm going to isolate the base and the exponent. So I want to isolate 10 to the x. I want to get that part by itself. So I'm going to do so by dividing both sides by 5. And when I do, I'm left with 10 to the x equals 550. And this is where logarithms really come in handy. This is the point of a logarithm, is to isolate that exponent. So I am going to rewrite this exponential equation in logarithmic form. I would say log, what's the base of my exponential? The base of the exponential is 10, so that's the base of my logarithm, log base 10. Remember, I'm isolating the exponent, so of 550 equals x. So I've solved for x. I've gotten x by itself. As an exact answer, I would say x is, remember that base of 10 I don't need to write, so exactly x is log of 550. If I enter that into my calculator, which is what I want to do, I get approximately and go 3 places after the decimal and use your proper rounding rules, 2.740. So as far as I'm concerned, this is the best possible answer. You've given me an exact answer and you've rounded it to 3 decimal places. Okay. In this next one, I already have the exponential base and exponent isolated. So there's nothing I need to do before I write it in logarithmic form. So I'm going to write log, the base of my exponential is the base of my logarithm. I'm isolating my exponent, so that goes on one side of the equation by itself. Now, there are 2 things that I see here that stand out to me. One is that the t is not by itself. So I do have one more step in order to isolate the variable t. But I also notice that this is log base e, which we know that we can write as ln, the natural log. So this is the natural log of 142 equals 2t. Now, to isolate the t, to get t by itself, which is what it means to solve an equation, I'm going to divide both sides by 2. And so as an exact answer, I have t is equal to the natural log of 142 divided by 2. I could have also written that 1/2 of the natural log of 142. And when I enter that into my calculator and I round it to 3 decimal places, make sure you find where that natural log button is on the calculator, I got 2.478. And again, this to me is the best answer. I use these means approximately equal to, so I use that symbol to show that I've rounded that answer. So I have an exact answer and an approximate answer. Okay, and that's all that was on page 11. And now we're going to go into more equations. So if you didn't watch the last video, I talked a little bit about the different forms of exponential equations that we use with word problems. And we start in 26a with the value of a house after t years. So here's my initial value, 100,000. So I start with that number, 100,000. And my multiplier is going to be that I keep 100% of the value of my house and I add on 30% per year. But I need to change that 30% to a decimal. So I move that decimal place to the left 2 places and I'm going to add 0.30 to the t. So I would write that 100,000 times 1.30 to the t. And that says start with 100,000. You have 130% of the value of the house after each year. So what's the value of the house when t is 4? So this is 4 years after now. And so I'm going to say v of, and this says I'm plugging 4 in for the amount of years. V of 4 is 100,000 times 1.30 to the 4th power. So I use my calculator to do that. And I come out with the value of the house being $285,610. And that's how I'd recommend you show your work. You want to show proper function notation, you want to show where you've plugged in the value, and then what you get when you evaluate that. Next, what is the average rate of change of the value of the house from the beginning of the year to the beginning of 2019? Be sure to include units in your answer. So, average rate of change is the slope of the line if the value of the house were to increase the same every year. So I'm going to say at time 0, I know that the value of the house is $100,000. And at time 4, the value of the house is $285,610. So if I want to know, on average, how much has the value of the house changed each year, I say, well, the value of the house changed $285,610 minus $100,000. That makes sense. It changed $185,610 over the course of 4 years. So you might remember from Algebra 1, this is the slope formula. y2 minus y1, change in y, over x2 minus x1. So this is change in y over change in x. Okay? And if I think about what the units are and the values, I get 185,610 divided by 4. And what are those? This is a number of dollars, and this is a number of years. And when I do that division, I get that the value of the house has changed $46,402.50 each year. So it's the number of dollars per year that the value of the house has gone up. And this next problem is kind of similar, except the value is decreasing. So if the boat is starting with a value of $1 million, it's going down over time. And that's going to come into my equation in the multiplier. My initial value is $1 million. This time I do 1 minus, and I'm going to subtract the 20% per year, written as a decimal. I'm going to subtract 20% of the value of the boat every year. And so really, if the boat is worth $1 million to start, my multiplier is 0.8, 80 hundredths. It is 80% of what it was the year before. So that kind of makes sense because we're talking about what value does the boat retain, and the 20% is what it loses. So if it loses 20% of its value after 1 year, it retains 80% of its value. So there's my formula. What's the value of the boat at the beginning of 2020? Again, think about how you're using notation. So proper function notation says we're plugging in 5. So I say v of 5. And then I'm going to rewrite my formula with a 5 plugged in for the t. And when I use my calculator to evaluate that, I actually put approximately equal to, but we actually get an exact answer. So let me go back. This is exactly equal to 327,000, that's a little bit better, $680. So that's how much the boat is worth after 5 years. So it's lost a lot of its value. If it started at $1 million and then it was worth 327,680. Now, at time 0, the boat was worth $1 million. At time 5, we found that it was worth $327,680. And they want to know, on average, what's the rate of change? Now, if you think about this just logically, the value of the boat is going down. So what's the average rate of change? It should come out to be a negative number because on average, the value goes down, okay? Change in y over change in x. I'm going to do y2 minus y1, $327,680 minus a million, over 5 minus 0, x2 minus x1. Now, if you're looking at that, I hope you realize that numerator is going to be a negative number, and that makes sense because the value of the boat is going down. So when I did this, I got negative 134,464. And they really want you to make sure you know the units. That shows that you know what you're talking about. So what are the units up top? This is dollars. And what is this down here? This is a number of years. So my units when I divide those are dollars per year. And you can either write it like this, or you could put the dollar sign in front of your answer like I did the last time. But that is saying that the value of the boat has decreased $134,464 each of the 5 years on average. Okay. Now we know that an exponential decay function actually looks like this. And so it's not linear. It's not going down the same amount every year. But if this is a million, that's 0, 1 million, and this is 5, 327,680. If we were to connect those with a straight line, that would go down, the line would go down $134,464 for each year that we went over this way. Okay? We are going to turn the page, and here we have compound interest problems. Now, what stands out to me immediately, here I have monthly. My interest is compounded monthly, and here it's compounded continuously. Okay, those are two slightly different formulas for compound interest monthly or n times a year. I use A equals P times 1 plus R over n to the nt. Okay, so P is my principal investment, $2,500. 1 plus, I'm going to take my 12% interest, that's a lot of interest, change it to a decimal, make sure you change those percentages to a decimal, 0.12. Compounded monthly, so I'm going to divide by 12 because I'm compounding the interest every month, so I only get 1% interest at the end of each month. And then I have 12 times a year for 4 years. So I'm going to get interest 48 times. Now, when you enter this into the calculator, that is usually the hardest part for students. Make sure you are very precise and you pay attention to the order of operations. I do this step by step. I do the 0.12 divided by 12, and I get 0.01. And then I add what's inside the parentheses. And I multiply this guy. And then I do 1.01 to the 48th. And then I multiply by the 2,500. And in this case, I got $4,030.57. With money, we go two places for the cents. And then think to yourself, does that seem reasonable? If Sammy deposited $2,500, could it possibly be that he'd have $4,030 after 4 years? All right, if he's getting a good interest rate like 12%, that might make sense. Okay, Jane down here deposits $4,000, and this is compounding continuously. So this is where we use A equals PE to the RT. And so we have a principal investment of $4,000, and we have a nominal interest rate of 7%. Remember, change that to a decimal, 0.07. And she is leaving her investment in there for 5 years. So again, pay attention to your order of operations. Multiply these guys out first, and then do e to that exponent. and then multiply by your 4,000. And I got that Jane will have $5,676.27. And again, think to yourself, is it reasonable that if she started with 4,000, she could possibly end up with a little more than 5,000? Yeah, that could possibly happen. All right, onward. So we are looking at logarithmic and exponential functions, and some things I want to point out about each of these before we go into the exercises is that exponential functions, this one is an exponential growth function. We can tell that either by the graph that is increasing, or we can look at the base here and say the base is larger than 1, so repeated multiplication of the number 2 will give us exponential growth. Over here, my other exponential function is a decay function. And remember, I look at that base and I want to say it's growth, but it's not, because you either think of this negative reflecting the graph across the y-axis, or this is 1/10 to the x, in which case the base is between 0 and 1, and repeated multiplication of the number 1/10 actually makes numbers smaller and smaller and smaller. Okay? But both exponential functions, you'll notice, have horizontal asymptotes. Okay? The parent functions of exponentials have horizontal asymptotes at y equals 0, whereas my logarithmic functions have vertical asymptotes. And vertical asymptotes have equations x equals, because every x-coordinate on this line has the same value. The x-coordinates are all 0. Okay? If I look at my exponential functions, I can plug any x value in here. So the domain is all real numbers. And because logarithmic and exponential functions are inverses, that makes the range of my logarithmic functions all real numbers. And if I look at the range of my exponential, you'll see that they start at your asymptote and go up. So my range starts at 0, does not include 0 because there's an asymptote there that I never actually touch. 0 to infinity is my range. If that's my range for my exponential functions, that's going to be my domain for these parent logarithmic functions. Okay? So these are some big takeaways. We'll refer to the graph as we go through these, but those are some important things. The last thing I will notice, or I'll have you notice, is the intercepts. Exponential functions have a y-intercept of 0, 1. Therefore, logarithmic functions have an x-intercept of 1, 0. Because on inverse functions, the x and the y are switched. Okay? So, which graph has a horizontal asymptote of y equals 0? Well, those are my two exponential functions, f and h. Horizontal asymptote, horizontal asymptote. And an asymptote is an imaginary line that the graph gets infinitely close to.
If you are still in the building, please stop by the main office to get your keys. Thank you.
Sorry about that announcement. Letter B, the function has a range of all real numbers. Remember, range is all of the y values. How low does the function go? How high does it go? So only the logarithmic functions. This one comes from infinitely far down, and it will grow, 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 grow. So this guy has a range of all real numbers. This one starts from way up here. It'll come down, and it will keep on decreasing. And so both of my logarithmic functions have a range of all real numbers. So that one is g and p. The function is increasing on its entire domain. So for increasing, decreasing, I read a function like I read a book, left to right. So this function is going up. It is increasing the entire time. This one is going up. it is increasing the entire time. This one is coming down, it is decreasing. This one is coming down, it is decreasing. Okay? The graph of the function has a y-intercept at the point 0, 1. So those are my two exponential functions, f and h. The domain of the function is the positive real numbers. So that means the domain is from 0 to infinity. And the ones that have that domain are my logarithmic functions, g and p. The graph has a vertical asymptote of x equals 0. Again, those are my log functions, g and p. The function has a domain of all real numbers. Those are my exponentials, f and h. The function is decreasing on its entire domain. So we already looked at that. Those were h and p. So logarithmic functions can increase or decrease. Exponential functions can increase or decrease. Just depends on the function. The graph has an x-intercept at 1, 0. That, if you look at how we've labeled them, those are my my logarithmic functions, g and p. And the range is the positive real numbers. So those are my exponential functions that never dip below a y-coordinate of 0. So the range, the y-coordinates, are only ever positive. So those are f and h. All right, and we are going to move on to page 15, where we are writing equations of transformations of the function e to the x. Okay, so remember that if there's anything in the x,
At this time, all students
remember that if there's anything going on with the x, that's going to have an impact on the x coordinates. So that's going to be a horizontal translation or a horizontal stretch or compression. If you have the whole function e to the x left intact and then you add onto it, or you have a multiplier out front, that's going to have an impact only on the y coordinates. So that's going to have an impact on the vertical part of the function. So when I want to translate one unit to the right, to go right, I need to impact the x coordinates. And so I am going to have e to the x minus 1. And the reason I have a minus 1, some people will say when you're doing something to the x's, just do the opposite of whatever you think it should be. So typically I would think translate one unit right, I would add 1. I do the opposite, so I subtract 1. That's a way to remember it, but that doesn't really explain why. In order for the function to be translated one unit to the right, I need all of my x coordinates to be one larger than they otherwise would be. And so to compensate for the fact that my x's will be larger, one larger, I need to subtract 1 in order to get the same y value. Okay? The asymptote of the graph has the equation y equals -4. Well, exponential functions usually have an asymptote of y equals 0. So this indicates that the function has been translated down 4 units. So to do that, I'm going to leave my function e to the x intact, and then only to impact the output, I'm going to subtract 4 like that. Okay? Reflecting across the x-axis, I want to negate all of my y-coordinates, which means that I'm going to put a negative in front of the whole function. And so all of my y-coordinates, or p of x coordinates, will wind up the opposite of what they otherwise would be. A reflection across the y-axis is actually, if you think about reflecting across the y-axis, this actually has an impact. It impacts your x coordinates, which is a little bit funny to think about. But to reflect from here to there, I need to negate my x coordinates. So I have e to the -x. Okay? And then finally, I'm looking at this last graph. I'm writing an equation for that. Still has an asymptote of y equals 0, so it hasn't been translated up or down at all. But I do notice that instead of a y-intercept of 0, 1, which is what I usually have, it looks like that point has been translated 3 to the right. And so I'm going to write the equation of e to the x translated 3 units right. So that's going to be e to the x minus 3. And again, my x coordinates need to be 3 units larger when it's translated right 3, so I have to subtract 3 to compensate there. Okay? And now I'm looking at a log function, and I'm doing the same thing. So translated 2 units to the left, that's going to impact my x coordinates. So I have log base 2, and I want to do something to my x coordinates. 2 units to the left, I actually need my x coordinates to be 2 units smaller, so I add 2. I have the opposite operation so that my x coordinates can be 2 units smaller than they otherwise would be. Okay? The asymptote is x equals 2. Well, usually the asymptote is x equals 0, and so this indicates that it is translated right 2 units. So to go right 2 units, I'm going to have log base 2. This time I'm going to say minus 2 because my x-coordinates have to be bigger when I go to the right. So I subtract 2 to compensate for that. Reflecting across the x-axis, I'm going to negate the entire function to make all of my p-coordinates negative. And then here, I notice that my asymptote is here at x equals 3, negative 3, and typically my asymptote is at x equals 0, so that has been translated left 3 units. And to write that, I have log base 2 of, and I need to go left 3 units, so my x-coordinates are 3 less than they otherwise would be, so I'm going to add 3 to compensate for that. Okay, and that's the end of Unit 1, Topic 3. Good luck in your studying and on your exams.